We're going to talk about magnetic fields and the forces they apply.
Potential energy or electric potential?
Electric potential voltage. Okay. We're going to talk about magnetic fields and the forces that they apply to objects. Now, these last 4 chapters, this last part of the year, it's pretty weird stuff. I don't think it's hard stuff. I don't think it's necessarily harder to understand or do the problems. It's just weirder. It's also at an awful time of the year when everybody's starting to get ready for their AP tests and it's the end and you guys are seniors and you're going through the process of becoming pathetic. And so, I mean, yeah, I've been watching it for a long time now. So what I want to do is to try to prepare your mind for what's going to happen to it when we study magnetism. You have to accept certain things as being facts, that this is the way it is, and understand it conceptually as well as be able to look at the mathematics for it. And then have little cartoons running around in your mind of, you know, what's happening here. And it is kind of weird. It's weird, but why should the universe not be weird? Okay? I mean, our brains are adapted to deal with a certain scale of size and time. But when you're dealing with magnetism, you're dealing with stuff that's happening to, you know, particles. Subatomic particles. Why should it make common sense? It's just not going to. The farther you go in physics, the weirder and the more wonderful it gets. I think it's more amazing than anything that Harry Potter ever had to deal with. Okay, so magnetism is very, very strange. But it's really wonderful, it's amazing, it's very important. We live in an electrical society. The way almost all the electricity we're using right now is generated is by using magnets and wires and the interaction of electrically charged particles in a magnetic field. So we use it to generate power. We use it to use it. So electric motors and generators and stuff like that. So it's really, really important. So let's begin by looking at a bar magnet. And this has a north pole. And this has a south pole. Now I'm going to assume that you've played with magnets before. And if you haven't, get some magnets and play with them. They're fun. Okay, and if you put the north pole and the south pole, you get an attractive force between those poles. Okay, and if you have a south pole and a south pole, or a north pole and a north pole, they repel. So it's kind of like what we dealt with electrostatic force. You know, like charges repel and unlike charges attract, but it's significantly different. Here we're dealing with poles. And what we say, it turns out that a magnetic field, it's going to come out of a north pole and into a south pole. Now you get a little bit of bowing outwards like this. Okay, but this is our magnetic field. Now you know that magnetic fields apply forces to objects at a distance, right? If you play with a magnet, it has an effect on objects or on material that can be magnetized. And so we're going to represent that effect at a distance as fields, as a field. And we've done this before, right? We've had gravity fields where we've drawn lines. And we've done electric fields now where we've drawn lines in space. And now we're just going to do the same thing for magnetic fields. Now for magnetic fields, we have a name for the strength of the magnetic field, how crowded they are. We call it B. That's our B field. And B is a measure of the strength of the magnetic field. So the stronger the magnetic field, the more magnetic field lines I'm going to draw. And we'll talk about the units for it here in a minute. Now, if I took some magnets, let's draw a magnet down here. Just a little bar magnet. And here it's the north side and the south side. We say the magnetic lines of flux will come out of the north, wrap around, and go into the south, and form a magnetic dipole. Okay, and some of them will go like this. But here's something about magnetic fields that's different than electric fields. Okay, we say they come out of the North Pole, but they don't really come out of the North Pole. What we're going to discover is that magnetic field lines come in loops. They always come in loops. So this, we say it comes out of the North Pole, but really what's happening is it's going back in, and all these magnetic field lines are traveling or actually extending into the magnet itself. Okay, so they come out of the North Pole and into the South Pole. Now I'm just describing them right now. I'm not telling you why there are magnetic field lines. I'm just saying that there are, and they behave like this. Now the fact that this magnet, this bar magnet, the magnetic field line comes out of the north, goes into the south, but then actually moves through it in a loop like this. This is why we never see north poles and south poles separated. You can't have a magnet that just has a north pole. If I break this in half, if I took a saw and just cut this thing in half, okay, what would happen if I cut this in half is that now I would have two magnets. If I took this and separated it, I just formed two magnets. Okay, you always have a north and a south pole in a magnet, with a magnet. Okay, these will go like this, and of course you might have some flux coming, out this way, and but it just, all you do is separate the magnet. So you just break it. They always come in loops. Magnetic field lines always come in loops. Now, the direction of a magnetic field line is defined by a compass. If you took a compass and laid it down on a magnetic field, it would point to the direction of the magnetic field line. So if I had a fairly strong magnet like this one, and I put a compass right here, it would point. Let me draw it better. It would point like this. It would point in the direction of the magnetic field, which is weird, right? If you have a compass, if you've ever used a compass, it points to the north, doesn't it? But we just said that magnetic field lines go into the enter the South Pole. So, well, I mean, all this was defined before we knew what we were talking about in terms of compasses and so on. And it turns out that the North Pole of the Earth is actually the South magnetic pole. Yeah. What? No, that's a joule per second. All right, so now, so this is all kind of interesting stuff about magnetic fields, but here's the main thing we're going to talk about today, is what influence do magnetic fields have on charged particles. And what I'm about to show you is something that's kind of weird, but yet you just have to accept it. Here's the weirdness for the day. If I put a positive charge, positive test charge, right in the middle of that magnetic field, and it's just sitting there, it's not moving, it's not going to feel any force at all. Now, if this was an electric field, it would feel a force, wouldn't it? An electric field applies forces to charged particles. This is a charged particle. It's in a magnetic field, doesn't feel anything unless it's moving. If it's moving, it will feel a force. Okay? Now this is experimentally, empirically derived, what I'm about to show you here. And it's absolutely true. And you really have to think about vectors. You have to think in three-dimensional space now with vectors. Suppose this little charged particle had a velocity and it was moving perpendicular to the magnetic field. It will feel a force. And the force that it feels, in this case, is going to be into the paper. So if I have a force that's into the paper, what I do is next to the charge, I'm going to put a little cross like that. This symbol right here means, hey, the vector's going into the paper. So this means into the paper.
Can it also be out of the paper, or is it just orthogonal, or is it specifically?
Okay, no, out of the paper, coming out, looks like that. This is a symbol for out of the paper. Whoops. Now, why is that? Why do we use this? Actually makes sense. If you shoot an arrow away from you, you see the tail feathers. These are the tail feathers of an arrow. If you see it coming out at you, into your eye, this is what you see. This is the last thing you see before an arrow hits you in the eye. Okay? So this means the arrow is coming at you. This means it's moving, going away from you. So this means, so what I would have here is I would have a force vector. I'll just draw it like that. And so there's my force into the board, or into the paper, I mean. There is an equation that accurately describes the force that a magnetic field applies to a moving charged particle. And that's this equation right here. And this is fundamental to magnetism. The force on a moving charge due to a magnetic field, we'll call it F sub B, is equal, well, the object has to have charge, and we'll call that charge Q. You double the charge, you'll double the amount of magnetic force acting on that object. It has to be proportional. The force is proportional to the velocity of the object. If it's going twice as fast, you'll feel twice as much force. This is what we observe. It also depends on the magnetic field. The stronger the magnetic field, the greater the magnetic force. That makes sense. Now, the direction. This is the part that you just have to accept. Everything here kind of makes sense based on the physics that we've done, except, well, why a moving charged particle? You get to that later. We'll get to that later. We'll get to the why later on. It turns out that the force, the direction of the force obeys the cross product between V and B. So this is Q, V, B, sine phi. Phi is the angle between the tail of your velocity vector and the tail of the magnetic field vector. And what's the direction? RHR. What does RHR stand for? Right-hand rule. You have to use the right-hand rule to figure out the direction. So what makes this hard for a lot of people is that you have to think in three-dimensional space for this. You know, almost everything we've done up till now, you can draw a cross-section of it and it can be put into two-dimensional space. Very difficult to do that with magnetism. You have to think in 3D. Okay. I wish I had a 3D camera. I could, you know, do it in 3D, but don't have a 3D camera. Someday. All right, now, actually, I bet we will be able to. 3D document cameras. All right. Now, so what I want to do is practice using this. Oh, before we get to that, though. Huh? Oh. Here's our pulsing cloud. All right. So yeah, you have to know this one, and you have to understand it. Now, let's talk about units. With electric field, we just used newtons per coulomb or volts per meter. We didn't have a name, but we do have a name for magnetic, the strength of the magnetic field. And it's called a Tesla. Teslas. So magnetic field strength, let's talk about units. B has units of Teslas. And we use a capital T. Now, how do we define a Tesla? I mean, what is a Tesla? Well, we use the equation to define what a Tesla is. Solve for B. Well, first of all, over here you've got newtons. And then you got to divide by coulombs. And you got to divide by meters per second. So there's my units for Teslas. Let's clean that up a little bit. Think of it as a Newton second per meter coulomb. Of course, a coulomb per second is an amp. We're going to get to that later. Okay, but these are the fundamental. Well, not fundamental, because what can we do to newtons? Yeah, kilogram meter per second squared, and we can get all that in there. But really, the way the strength of the magnetic field is really a function of how much force do you get per unit charge per how fast it's moving. And once you get used to this, that kind of makes sense. This is the way to think of it right here. This is just getting a little more simplified, but the way I like to think of a Tesla is if you have 1 Tesla, you get 1 Newton of force for every coulomb meter per second of charge and velocity you have. And okay, those are the units for it. So now what I want to do is show you, do a couple of drawings, and what I want you to do is get used to using that right-hand rule, okay? Because it just takes a little bit of practice. I'm going to give you 4 problems to do. And I'm going to just draw a magnetic field, give it a charged particle in there, give it a velocity vector. You have to figure out what the force is, what direction it's in anyway. Okay, so suppose I've got a magnetic field that looks like this. Here's B. And let's say that the velocity vector is in to the board, like that. Okay, so we'll call this, we'll call this example 1. Or let's do example 2. Here's my magnetic field. And let's put a little positive test charge. Oh, let's say this is a positive test charge too. Here's my velocity vector. So here's V and B. Find the force. Find the force. All right. Let's have a magnetic field coming out of the board over here. We'll just do 4 of these. And let's have a velocity vector moving straight down. And that'll be example 3. So figure out that. And then over here we'll have a magnetic field like this. And then I'll put a positive charge here. And here's my velocity vector like that. So what I'd like you to do right now in your notes is draw the force vector on here. Show the direction of it, and just with a force vector. Okay, so, and now remember to use the right-hand rule. When you go V cross B, okay, you take your right hand, and here's my right hand, and let me zoom a bit here to make it. You take your right hand, this is the way I do it. There's lots of different ways of doing the right-hand rule, but this is how I like to do it. You take your right hand and you orient it in the direction of the velocity vector first. Now you can rotate your hand like this as long as your fingers point in the direction of the velocity vector. And then you cross your hand into the direction of the magnetic field. However, if the magnetic field is now you can turn your hand like this, you can rotate your hand but you have to turn your fingers towards the direction of the magnetic field. Your thumb will point in the direction of the force. Okay, and this is just the right-hand rule for all cross products, right? You point your hand in the direction of the first one. You may have to turn your hand over. You may have to do a little, you may have to turn your body over to try to get it the right angle. It's really fun to watch the exam for this. When you guys do the exam for this, because I got people that are just, they look, well, Elaine in Seinfeld?
Oh, what's Elaine?
When she dances, you guys kind of look like Elaine dancing, just with your right hand. Oh, by the way, those of you that are left-handed, you have an advantage. If you're right-handed, you have to remember to put the pencil down, use the right-hand rule, and then pick the pencil up. Because if you use the left-hand rule, if you use your left hand, your answer's in the opposite direction. Your thumb's pointed the wrong way. Okay, so I'm going to... Now, if you're watching this at home, because half the class is absent today, pause the video right now. Oh, actually, this will be the end of the video. Yeah, because I'm gonna give you guys a chance to do it. So, too bad.